Okay, maybe we could quiet down a little bit. I'm going to start, because I think we're already a little bit over time, so if you don't mind taking your seats. So let me just go back a slide so that we can remember what we were doing. So the goal now was to prove hardness of classically simulating a random quantum circuit. In all of this discussion before this, to be clear, we were talking about worst case quantum circuits. We were not talking about random circuits. And so what I told you is the goal was to argue about the hardness of this problem, right? Where we're given as input a random quantum circuit drawn from the distribution I described way earlier in the talk, where the 2-qubit gates are random. And then the goal is to output an estimate that I was calling Q to the output probability of that circuit to within imprecision delta. Okay? So again, this problem in the blue box, it has sort of two weaknesses that we haven't discussed yet, right? One is that it's an additive approximation, and two, it's an average case additive approximation. It only works with high probability over the circuit. Okay? And then I said that the goal of this sort of whole theory of quantum advantage community is to prove that this particular problem is hard when this delta parameter, which I call the imprecision, is 2 to the minus n, where n is the number of qubits that the circuit acts on. The reason 2 to the minus n is really important is because it's 1 over the Hilbert space dimension. Okay, now I then sort of gave you this timeline, and I said, we haven't been able to get there yet, right? What we can do is, in the beginning, we showed a hardness result at delta equal 2 to the minus m to the fourth. That's gotten better all the way through 2 to the minus o of m, but that's still off by at least a constant factor in the exponent from what we want. Okay, so then I was talking about how do we show average case hardness. In fact, here we were talking about average case exact hardness. I was talking about delta equals 0, in fact, right? And I was saying, well, there's only really one way to do that, and that comes out of this result of Lipton, who is studying the average case hardness of computing the permanent of a matrix. Okay, so in other words, the question is, how hard is it to compute the permanent of a random matrix with high probability? Is it considerably easier than computing the permanent in the worst case? And what Lipton shows in the early 90s is that, in fact, they're of the same difficulty. If you have a faulty algorithm that computes the permanent with high probability over a random chosen matrix, you can use that ability to compute the permanent of whatever matrix you like. Okay. So how did this work? Well, we used this sort of algebraic property that the permanent was a degree n polynomial in n squared variables, which were the matrix entries. And we then had a very simple sort of polynomial extrapolation argument. So the way it worked is we chose n plus 1 fixed non-zero points in our field, and then a uniformly random matrix R. And then we looked at this line, which I called A of t, which is x plus t times r. Okay, so we take our worst case matrix and we shift it by something random. And we had two observations. One I call the scrambling property. It's that for each I individually, A of t sub I is scrambled. In other words, it's a uniformly random matrix over our field. And then observation 2 is this univariate polynomial property, so that the permanent of A of t is a degree n polynomial in the single variable t. And these two observations together lead us to our proof in a straightforward way. What we do is we use the faulty algorithm O to evaluate the permanent of the matrix A of T1, A of T2, and so on. Then once we have n plus 1 points, well, by the fundamental theorem of algebra, the polynomial is of degree n, so this uniquely specifies this permanent of A of t polynomial. Once we know the coefficients of the polynomial, we can then evaluate it at t equals 0, which gives us back permanent of our worst case point, right? Okay, great. So that's where we left off. Okay, so now what we really care about is not the permanent of a random matrix, but rather the output probability of a random quantum circuit. So, how do we adapt Lipton's argument from talking about the permanent of a random matrix to the output probability of a random circuit? Well, this was the goal in our 2018 work. And one thing we started noticing when we thought about this problem is that there's actually a lot of similarities between the permanent on the one hand and the output probability of a random circuit. In particular, there's this simple algebraic property, which is much like the permanent. The output probability of a random quantum circuit has polynomial structure. How do I see this? Well, let's say I take the circuit, C, and I break it up into its 2-qubit gates. So that's what these CM minus 1 through C1 are, just 2-qubit gates. M is the size, it's the number of 2-qubit gates. Now, the polynomial structure comes from the Feynman path integral, which allows us to write the output amplitude of the circuit, right, as an enormous sum over paths, right? So there's an exponential number of paths, but the point is that the value of each path is just the product of m gate entries, right? That's what these terms are. They're just the product of m gate entries. Those are easy to compute. So even though this sum has an exponential number of terms, right? The value of each path is actually doable in P. You can compute that very easily by taking the product of m gate entries. Okay, so not surprisingly, this is a polynomial of degree m in the gate entries of the circuit. Okay, and so by the Born rule, the output probability, which we were calling P0 of C, is a polynomial of degree 2m. Right, we just square the amplitude. Okay, so now let's try to use this polynomial structure to prove the average case hardness of computing the output probability of a random circuit very much in the way that Lipton does. Okay, so how are we going to do this? Well, actually, first let me talk through this. So what is the goal? Right. Well, the goal is you give me a worst case circuit, whatever your favorite circuit is, your quantum circuit, and you ask me, to compute the output probability. Well, of course, I don't know how to do this, but I happen to have, by assumption, an algorithm that works to compute the output probability of most random circuits, with, say, probability 2/3. Okay? Now, the goal, just like in Lipton's proof, is I want to use the ability to compute, the assumed ability to compute the output probability of a random circuit, right, to compute the output probability of my favorite circuit, C. Okay, so what's the strategy here? How would I do this? Well, very much like Lipton, I want to take this circuit and I want to scramble it. I want to make it look random. Why do I want to make it look random? Because I have the assumed ability to compute the output probability of most random circuits. So it makes sense that I'd want to scramble the circuit. So how are we going to do this? Well, we're going to fix m Har-random 2-qubit gates. So I'll call them H1, H2 through HM. One Har-random 2-qubit gate per ideal gate of the circuit, C. So there's m gates in the circuit, so we have m Har-random gates. Okay, and then the main idea is to scramble by implementing a tiny fraction of the inverse of these gates, right? So here's what I mean. So remember the gates of my worst case circuit are these CIs, okay? So for each gate, CI, in my worst case circuit, I'm going to consider a scrambled circuit whose gates are called CI prime, okay? And the way I'm going to get CI prime is by sort of doing two things. So first, I'm going to take the ith gate of my worst case circuit, CI, I'm going to multiply it by HI. That's a Har-random gate. And now, by the invariance property of the Har measure, if you take a fixed gate, right, and you multiply it by a Har-random gate, the result is Har-random, okay? So, if I just take CI times HI, I've completely scrambled this circuit, okay? But I'm going to do something a little bit more clever. I'm not just going to completely scramble the circuit. I'm then going to multiply by e to the minus I little hi theta, where I'm thinking of little hi here as the log of my Har-random gate hi, okay? So now I'm going to claim this is sort of an interesting way of scrambling a circuit, making a worst case circuit C look more random, that sort of has a property a little bit like Lipton, in the sense that this complete, if we take theta to be really close to 0, then it essentially scrambles the circuit completely, right? Why is that? Well, if we take theta to be very close to 0, this e to the minus I little hi times something very small, does essentially nothing, right? So we're left with something that's essentially CI times HI, which is scrambled. Okay, that's a totally random circuit. On the other hand, if theta is equal to 1, so if it's not small, right, then if you look at what we have, Well, what we're doing is we're implementing Ci times Hi, it's completely scrambled, but then we're multiplying back by e to the minus I little hi times 1. Well, by definition, e to the minus I little hi is hi inverse, and so we get back our worst case circuit. We get back all of the worst case gates of our circuit C, okay? So this is what I mean when I say this has a very Lipton-like feeling to it. It's sort of, if you're taking theta values that are really small, then the circuit C theta looks really random. If you take theta that's very large, like close to 1, it's not only not random, it looks like C, the worst case circuit, okay? So what are we going to do with that? Well, the strategy then would be something like this. So let's consider taking several non-zero but small values of theta. So we'll call it theta 1, theta 2, and so on. And let's say that we use our, we're assuming that we have the ability to compute the output probability of a random circuit. So what we're going to do is we're going to use that ability to compute the output probabilities of C of theta 1, C of theta 2, and so on through C of theta 2m. 2m is important because that's the degree here. It comes from the path integral. Okay, so now we have these 2m points. We uniquely specify the polynomial by the, we use polynomial extrapolation to, to reconstitute this polynomial. And then the goal is to evaluate it at theta equal 1, because when theta is equal to 1, we get back our worst case circuit. Okay? Now, that's not completely correct because it's not actually super clear where the polynomial structure comes about, right? So there's sort of a problem here, which is that e to the this gate we used, e to the minus I little hi theta. We were thinking of little hi as the inverse of big hi. Sorry, the log of big hi. It's not a polynomial. It's not a fixed degree polynomial in theta. It's just not. And so the solution that we proposed, which actually causes a lot of issues down the road, but I think it makes sense from the point of view of what we're trying to do here to get a polynomial. We propose taking the fixed degree Taylor series truncation of e to the minus I little hi theta. So in other words, here's the final way we propose taking our worst case circuit and scrambling it, making it look more random. Right, so what we do is we take each gate in the worst case circuit, Ci, we multiply it by hi, and then multiply not by exactly e to the minus I little hi theta, but rather the kth order Taylor series truncation of this gate. Okay? Okay, now why do we like this? Well, we like this because now each gate entry is a polynomial in the single parameter theta because the Taylor series is a polynomial in the single parameter theta. And then by the Feynman path integral, all we're doing is writing the output amplitude as a sum over products of the gate entries, right? So, because of that, the output probability also becomes a polynomial in theta, okay? Right, so then the whole point is we now take more points than the degree. The degree is like 2m. We extrapolate to, reconstitute the polynomial, and then which we're calling p, and then evaluate the polynomial at 1 to get back our worst case circuit. This is very much the equivalent of what Lipton did. But there's sort of a big issue here, which is how do we motivate these Taylor series truncations? I mean, if you think about what the Taylor series truncations are doing, on the one hand, they're giving us the polynomial structure that allows us to use Lipton's result to prove that the hardness of the worst case circuit. But on the other hand, they're actually leaving the unitary group slightly, right? If you think about what's going on, the new distribution that we're proving hardness for over circuits is actually, supported on circuits that are ever so slightly non-unitary, right? They're non-unitary because we took the Taylor series of a unitary operator and we truncated it. We just lost a whole bunch of terms. I would say that like 2/3 of the technical work in this 2018 paper was to justify that this was okay. And so the way we did this is sort of the following. Remember in my first slide on this subject, the goal was not to show the hardness of exactly computing the output probability of a quantum circuit. Rather, it was to show the hardness of estimating the output probability of the circuit to some imprecision delta, and I said we really wanted to take delta like 1 over dimension of Hilbert space, which is like 2 to the n, okay? And so we're really interested not in the hardness of exactly computing these output probabilities, but in the hardness of estimating them. And what I see as sort of our main technical result from our 2018 paper is that we say, well, if the goal is to estimate these output probabilities, then in fact, it doesn't matter if we're talking about the hardness of estimating the truncated probability, which is talking about a circuit that's ever so slightly non-unitary, or the hardness of computing the unitary random circuit. Right? In fact, it's an if and only if. And why is that? Well, I'm not going to prove that here. It's quite technical, but intuitively it's because the error we're making by truncating our unitary operator is so much smaller than the additive error we're conjecturing is hard. If you look at my interval picture here, sort of my cartoon of what's going on, what we're actually showing is hard is this output probability that I'm calling C prime, which is the truncated circuit. It's slightly non-unitary. What we want to show is hard is this thing that's very close to it, which is the output probability of the unitary circuit C. Okay? But then we're making this conjecture that outputting any point in this much wider interval, right, of width 2 to the minus n over poly, or say, big O of 2 to the minus n, is hard. And so somehow the moral is, if we're really making a conjecture that outputting any point in that much wider radius or distance is hard, then somehow the really small distance between the output probability of the unitary circuit shouldn't matter that much from the output probability of the truncated circuit. In fact, we prove this, but I think luckily for everyone involved, you don't even have to go through this anymore. It's largely historical, and the reason is because follow-up work to this by Rami Smovisag showed a related argument using what he calls the Cayley path that actually eliminates the need for these Taylor series truncations altogether, which is actually a very nice result. The idea is very similar. In fact, it uses a Lipton-like proof where we're simply, what are we doing in Lipton? Well, we're taking sort of a single parameter path through the unitaries that starts in the worst case unitary and ends in some random unitary, right? And we gave one path, one way to do that, one single parameter path, the parameter we called theta, that happened to be, sort of ever so slightly leave the unitaries. But Ramis's path, actually stays unitary throughout. And so what's really nice is that, using this path, Rami's could probably have reduced our paper in like half the length, something like this. Okay, great. But so far we haven't been talking about imprecision. We've been assuming that this algorithm that sort of works to compute the output probabilities of a random circuit, when I say works, I mean exactly computes the output probabilities. Now, right, the output probabilities of these random but scrambled circuits, which I'm calling C of theta 1, C of theta 2, and so on. But our actual setting is approximate. So what we're actually given is 2m evaluation points, which I'm going to think of as a pair, theta I and yi, with the property that for all I, this ith evaluation point, delta approximates the output probability of the ith circuit. Okay? So in other words, in the prior discussion, when we were talking about Lipton's argument and how to adapt it, we were assuming delta was 0. Okay? But what we're actually interested in is much larger deltas, like on the order of 1 over 2 to the n, where n is the number of qubits. And so in reality, we sort of have two polynomials. The ideal polynomial, right, that we don't actually have direct access to, right? This is the polynomial so that, for every I, the P of theta I is exactly equal to the output probability of the ith circuit. And furthermore, when theta is equal to 1, P of 1 is exactly equal to the output probability of the worst case circuit, which is what we're trying to find. Okay, but no one gives you P explicitly. Instead, what we have access to is what I'm calling the extrapolated polynomial, which we're going to call Q. That's the polynomial so that the ith entry, the Q of theta I is equal to the ith evaluation point. Okay, but these evaluation points, though, they're approximate. right? They're not exactly the output probability of the ith circuit. They're a delta approximation, okay? So the real question is actually very easy to state mathematically, which is that if we have these approximate points, right, and we use them to extrapolate our polynomial, right? How close are these if these points are very close to the actual polynomial, they're like delta close at some narrow subinterval of the unit interval 0 through theta max, right? Then how close is the polynomial? How close are the two polynomials all the way over at theta equal 1? Okay, because that's the evaluation of our worst case circuit. That's what we want to compute. Okay. So it turns out the answer to this question lies in what we call the Paturi picture, which is, which we call in honor of Paturi, whose 1992 result in approximation theory was really foundational and answers this question directly. So here's what he says. It's just a mathematical theorem. It says if you have a degree d polynomial, I'll call it z of theta, bounded on a tiny interval of the unit interval 0 through theta max by little delta, then all the way at 1, the z of 1 has to be less than or equal to delta times 2 to the degree times theta max inverse, 1 over theta max, okay? So what is our case? So how does this apply to our theorem? So what we're going to do is we're going to consider the degree 2m polynomial, which we'll call z of theta to match with my the Paturi theorem, which is going to be the difference of the ideal polynomial p and the extrapolated polynomial q, okay? So, in other words, sort of the z is the polynomial that expresses the amount of error that we're making at, a polynomial, at a circuit specified by theta, okay? And, in our language, the picture sort of looks like this. We know that, when theta is really, really small, like it's smaller than what I'm calling theta max, okay? Well, then the output probability, the corresponding circuit, c theta, is very close to a random circuit, right? And our error is delta. So we're going to bound this polynomial z in this small box of height delta and width theta max, right? And then what we're interested in is how large can this polynomial be at theta equal 1, right? What Paturi says is that the answer is delta, that's the height of the box, right? The height of the little box, times 2 to the d times theta inverse max, okay? So in other words, if the goal, which it is, our goal is to make z of 1 smaller, because z of 1 is the error of our worst case circuit, there's sort of two parameters that we should be trying to manipulate here. We should be trying to either reduce the degree of our polynomial or increase theta max, right? Because if we increase theta max, then we're decreasing 1 over theta max, right? And that's showing up in the exponent of this, of this value of z of 1. Okay, so reducing the degree of the polynomial seems very tough, right? Because the polynomial is given to us, it's sort of set by the Feynman path integral, right? It's difficult to find what another polynomial would look like, but we should ask, what is setting our parameter for theta max? That's the width of the box, right? What is constraining that? So what is constraining that? Well, this sort of naive polynomial extrapolation argument, which I'm calling Lagrange extrapolation, that's the polynomial extrapolation you learn in grade school, requires getting all 2m points exactly correct, okay? So there wasn't any room for error, and because of that, we were invoking a union bound, right, which said that as long as the algorithm, the faulty algorithm, succeeded with probability 1 minus something like 1 over m, then all of these 2m points were going to be correct with probability 2/3, okay? And so that required taking this algorithm to have very high success probability, right? Because otherwise, there would be a significant chance that the algorithm would be wrong on some point, and we wouldn't know how to use Lagrange extrapolation for that point. Okay, but let's think about what that means in terms of the way we just showed about scrambling our circuit, right? Well, we sort of want to take theta max to be as large as possible because we really want our, the points that we're considering, our extrapolation points, to be very close to our worst case point, Right? That's going to minimize the blow up, this Paturi blow up. Okay, but the problem is you have to be really careful when you do that, because if you think about the way we're extrapolating, as theta gets larger and larger, right, our circuit, the scrambled circuit, C theta, is actually further and further away from a truly random circuit, right? So for example, when theta is equal to 1, it's not truly random at all. It's our worst case circuit, right? So this argument somehow should only work when theta is sufficiently small. So how do we make this rigorous? Well, it turns out we can, so this is a calculation that I'm not going to go through, but we can ask how close is the distribution of the circuit, C prime theta, to truly Haar-random circuit, right? And it turns out we can express an upper bound in the total variation distance of m times theta. So in other words, for each gate, we're sort of adding a theta factor, okay? Okay, so now, what that means, it turns out, is that you can show that the algorithm, the faulty algorithm, if it worked before, say, with probability 1, which it didn't, but let's just say it did, then it works with probability 1 minus m times theta on these points that are not exactly Haar-random, because the guarantee of the faulty algorithm was only that it works with high probability on a random circuit. Okay, so we do algebra and we conclude we have an algorithm which works with probability 1 minus m times theta. We want m times theta to be 1 over m, so we can use Lagrange extrapolation. So that means that we need the largest theta we choose to be less than or equal to 1 over m squared, right? So that m times 1 over m squared is equal to 1 over m. Okay, now we plug in Paturi's bound, and we have our degree, which is on the order of m, that comes from the Feynman path integral, and we have our bound for theta max, which is, we have to be less than or equal to 1 over m squared, and what we get is that z of 1, the error we make on our worst case circuit, is delta times 2 to the m cubed. So to compensate for this exponential blowup in m cubed, we need to take delta equal to something like 1 over 2 to the m cubed, okay? So in fact, this answers the question of how robust our original results were, okay? So they're not actually that robust. They have an exponential and m cubed factor to them, okay? Okay, so now, here's what we're going to do. So to improve the imprecision of these results, to make it larger and larger delta, we need a new sort of more error-robust means for polynomial extrapolation, okay? Because, the whole culprit, the reason that the past argument was so sensitive to errors was because we were using Lagrange extrapolation, which required all of the points to be correct, okay? So to improve the situation, we're going to need a more error-robust means of polynomial extrapolation, and we're going to do this by oversampling. In other words, in the Lagrange picture, we sort of use as many extrapolation points as the degree, okay? But in fact, what we're going to show is you can do a lot better if you're willing to take far more points than the degree of the polynomial, okay? And here's the theorem that we prove. We call this the robust Berlekamp-Welsch theorem in honor of a similar theorem that was known in the context of classical error correction, called the Berlekamp-Welsch theorem. Anyway, so what our theorem says is the following. Just a mathematical theorem again about polynomials. It says, suppose we're given on the order of d squared faulty evaluation points to a polynomial p of degree d with two properties. So first, each one of these points lives in this tiny subinterval of the unit interval of 0 and 1 over d. Okay? It's actually 1 over d is important for this argument to work. Two, we know that at least 2/3 of these points delta approximate the evaluation of the true polynomial. Okay? So in other words, 2/3 of these points, theta I, yi, are such that yi is a good delta approximation to the output probability of the I circuit, but then there's 1/3 of these points that might be very far away from any of the circuits. Okay? Now, here's what we show. So we show that suppose someone else gives you another polynomial, okay, which we call Q of theta. The only thing they tell you about that polynomial is that polynomial is also delta close on a potentially different 2/3 of these points. Okay, it doesn't have to be the same 2/3. It's just that within this narrow subinterval of the unit interval, this polynomial is delta approximates some 2/3 of them. Okay? Okay. Then what we show is that, in fact, anywhere in the interval, for theta anywhere between 0 and 1 over d, the maximum distance of the evaluation of q of theta and the evaluation of p of theta is delta times 2 to the O of d. Okay, so let's look at the picture here. We sort of have a black polynomial. That's p. That's the polynomial we want to understand. We're promised that, we're not given p explicitly. That would be too easy. Instead, we're given these red evaluation points and promised that 2/3 of them are delta close to the curve, to p. Okay? Now we're saying, okay, suppose someone comes along and they give you this blue curve. Okay, that's q. Okay? Now, the only property we know is that q, is delta close to 2/3 of the points, but it could be a different 2/3 of the points from what p is close to. And we say no matter how this q acts, if we look at this tiny subinterval of the unit interval of width 1 over d, the most these two polynomials can differ in that subinterval is delta times 2 to the O of d. Okay, so that's our theorem. So now why does it help us? Well, it turns out it's going to help us take theta max to be larger, which is what we want. Okay, it's going to reduce the error on our worst case evaluation. Okay, so let me remind you of why. So again, what's the input? Well, you should think of it as faulty points to a polynomial p of theta. We'll call it theta 1, theta 2, and so on. And what we know about these points, of course, is that 2/3 of them are delta approximations to the polynomial p of theta, right? Okay, now we're using an NP oracle anyway because Stockmeyer's algorithm used an NP oracle. So it's actually fair game to use an NP oracle, and we're just going to ask the NP oracle to give us a polynomial, the coefficients of a polynomial q that's delta close to 2/3 of these points, okay? Now, it's actually sort of interesting. The reason this is an NP problem is that it's easy to check that a polynomial that the oracle gives us is close to 2/3 of these points. How do we do it, right? Well, we simply evaluate q, the polynomial that the NP oracle gave us, at each of these points and make sure they're delta close at 2/3 of them, okay? One thing, of course, we can't check is whether q is close to p, right? That's hard to check, but we can check that the polynomial q that the NP oracle gave us is close to 2/3 of these points. And so now we're going to plug in the theorem we just proved, or I showed in the last slide, what we called the robust Brillouin-Welch theorem. And it tells us that, anywhere in the subinterval 0, 1 over m, these two polynomials, p and q, agree to within a factor I'm calling delta prime, an additive factor of delta prime, which is delta times 2 to the m. To m because that's the degree, okay? And now we can plug in Paturi, right? And we see that the advantage we have here is that the theta max is now 1 over m, right? So if we just plug and chug, we have that the error that we're making at the worst case point, which we're calling z of 1, is upper bounded by delta prime times 2 to the O of d times 1 over theta max, which is delta times m squared. Okay, correspondingly, you can now take delta to be 1 over 2 to the m squared, so we gained a factor of m in the exponent. And remember the last time we had 1 over 2 to the m cubed. Okay, now, that's actually not the state of the art. The state of the art is around 2 to the minus O of m log m, and it uses a simple trick together with this robust Brillouin-Welch theorem. Which is the following. So remember, I'm just repeating this. What is the input? We're given faulty points and promised that 2/3 of them delta approximate our polynomial. And now here's the trick. So before we ask the NP oracle for the approximating polynomial q of degree m, that also 2/3 agrees with these points. Okay? Now we're going to do something a little bit more clever. Rather than asking the NP oracle for a polynomial q that delta agrees with 2/3 of these points, we're going to ask for a slightly different polynomial that we call the rescaled polynomial, right? And that's going to be the polynomial that comes from replacing the extrapolation variable theta with x to the k for some large k. And we're going to ask for this polynomial, so which I'll call q prime of x. So another way to think about this is, rather than giving the NP oracle these points, theta 1 and y, and theta 2 and y, and so on, and asking for an approximating polynomial, we can instead give the NP oracle the points theta to the 1 over k, theta 1 to the 1 over k, theta 2 to the 1 over k, y2. So, sorry, just to be clear, we're keeping the y's the same. So we're asking the NP oracle for an approximating polynomial to the points theta 1, y1 to the 1 over k, theta 2 to the y2 to the 1 over k, and so on. So we're just rescaling the polynomial. Well, why does this help us? It's a little bit subtle. So first of all, this is increasing the degree. So if we had degree that was around m, we're now increasing the degree to k times m. Okay? That sounds like it should be bad. In fact, it's a little bit ironic, because remember, the degree was in the exponent of the Paturi bound. So it seems like we should be reducing the degree. Instead, we're actually increasing the degree from m to k times m. But what it does for us is it sort of stretches the unit interval near 0 and compresses near 1. So for a fixed value of theta max, which was equal to 1 over m, the corresponding value of x max is now a lot larger. It's like 1 over m to the 1 over k, right? So what it did is it sort of allowed us to take theta max, so to speak, which we now call x max, the width of the box, much, much larger. And when we plug that into Paturi's bound, what we see is we get a net advantage. We get that z of 1 is less than or equal to delta times 2 to the k times m, that's the new degree, that's d, times theta max, which is m to the 1 over k. Now, why does that help us? Well, if we plug in k equal log m, right, then what we see is z of 1 is less than or equal to delta times 2 to something that's around m log m. So we're just suppressing here the m to the 1 over log term. That's smaller asymptotically than the other terms. And so what it tells us is that we need to set delta equal to 2 to the minus o of m log m to compensate for this blow up. Okay? And that's what gives us the state-of-the-art robustness for outputting for arguing about the hardness of outputting estimates of random circuit amplitudes. This is a great place to stop, and I know this is technical, so I'm very happy to take questions.
Why do you have to ask this NP oracle about the interpolation and not do some, I don't know, robust L1 interpolation thingy or something like that?
Yeah. That's okay. Fantastic question. This is an open question. Like in other words, doing this without the NP oracle is open to the best of our knowledge. It's okay. I should say the Crovey result that I quoted earlier, which gives the claim of 2 to the minus m robustness, claims that they can do exactly what you were saying. So rather than an NP oracle, they can actually have an efficient algorithm for this robust extrapolation. Unfortunately, we haven't been able to verify all of that paper yet, but there is a claim made that one can do that. For us, it doesn't matter just because we were already using an NP oracle, so we may as well just keep using the NP oracle. But I don't see any reason why you can't, in principle, be smarter and make it an efficient algorithm. Can I get more questions?
When you mentioned Lipton's result, you mentioned that there was some lot you had to be able to compute most permanents.
Yes.
So it was like 1 minus 1 of a poly n. Is there a similar constraint with computing the output probabilities for these circuits?
Great question. If we were using the Lagrange extrapolation, the sort of grade school polynomial extrapolation argument, you'd have exactly the same problem that Lipton did, and you would absolutely need to, keep most of the permanents in your lane. You work with probability 1 minus 1 over m, right? However, the whole point of this, there's many points of this robust Berlekamp-Welch, but one side effect of this is this allows us to not have to do that, right? So this also increases the, allows us to work with a faulty algorithm that works with probability 2/3 rather than 1 minus 1 over m. Right, so it fixes that problem. Next.
Hi. So in one of the slides, you wrote the circuit expectation as a path integral in the previous slide.
Sorry, can you say one more time?
In the previous slide, the circuit expectation was written as a path integral.
The output amplitude, yes.
Yes. So what would be interpreted as the weight of the path of a given path?
Yeah, good. Okay, let's go back there. Oh, that was a long time ago, wasn't it? Anyway, what we were saying is that you can write the output amplitude in the Feynman path integral as a sum over paths of the product of m gate entries, right? That was that was what the Feynman path integral allowed us to do. The weight of the path for us would just be the product of those m gate entries. That's all it is.
But since the unitaries were truncated and we in some sense use completeness, how do you make it well defined?
How do you make it verified? I'm not sure I understand.
Well defined.
How do you make it? Say one more time.
Well defined.
Well defined. Ah, yes. Good. It's not clear that it's well defined. You have to prove that, right? And in fact, that's one of the major things that we had to do in our proof, that in fact, from a complexity point of view, the truncations don't matter. But it's not obvious at all. Yeah.
May I ask something about exactly the same theorem? So does it work for random circuits or for every circuit? That's what's not clear to me.
Good. No, so what it says is the following. It's very much like Lipton's proof. It says, let's say we have an assumed ability to compute the output probability of most random circuits. That's what you have one box that does that. Then what we're showing is how to use that ability to compute the output probability of any circuit. In other words, simulating a random circuit is as hard as simulating any circuit. That's what we're proving. Okay, two more.
Hi, I have a question about, so it seems like you're doing a lot of work because you have an imperfect, you have these faulty points and you're having to correct for them. I just missed in the very first use of Lipton how you didn't have to deal with these faulty points, because you also had an imperfect algorithm that got the permanent on most things.
Right.
But then you just took n+1 points and you were able to...
Yes. That's good. That's a great question. So so what we use is a union bound. We were saying that what we want is to for the algorithm to be correct on one more point than the degree, like say m+1. And we said if the faulty algorithm works with probability 1 minus say 1 over 6 times m or something like that, then with constant probability the algorithm will actually be right on all the points. Right? And so at the end of the day, we will then be able to, with very high probability, compute the permanent just by taking a sort of majority vote. Right? That's what we showed. Because of that, in the original, when I first explained Lipton, we didn't have to talk about these faulty points, because essentially we could union bound them away. We could say they're all correct with probability 2/3. Later on, when I wanted to improve, have a much more sophisticated result where we were sort of talking about, the robustness and dealing with these faulty points, we then had to, have this sort of robust Berlekamp-Welch theorem, which allowed us to be correct at merely 2/3 of the points rather than at 1 minus 1 over m of the points. Maybe one more? Yeah.
Thanks for the talk. So you have shown the robustness band for impossibility for classical algorithm, that is m log n.
So I can't hear. What is it?
You have shown now you have an impossibility of classical algorithm.
Yes.
That is to the power of m log m, right?
Yes.
So my question is, what's the best classical algorithm currently? Is it tight or not? So what's the best scaling and how much we can hope?
Good. No, we don't. That's a great question, and we actually don't know anywhere near a classical algorithm that works anywhere near like this. The best thing we can do is say for certain subclasses of circuits, not general random circuits, but certain subclasses of circuits, maybe it has very shallow depth or something like this. Yes. There are sometimes algorithms that can get close to this, make this tight, but not for general. For general random circuits, we don't have matching classical algorithms.
Okay.
Yeah.
Thank you very much.
Okay, why don't I keep going? Okay, so I just wanted to end maybe by some comments. So, the main point I want to make here is that, we've made a lot of, the last, say, 10 years, we've improved this by quite a bit, but we're still not where we want to be. The main goal, again, of, was to prove hardness of sampling. And to prove hardness of sampling, we required a 2 to the minus n robustness, whereas the best thing we can do right now is prove something like 2 to the minus O of m, where m is the size of something like n times d. Okay, for boson sampling, things look a little bit better. The similar arguments to what I just showed you show that we can, show hardness for delta equal 1 over e to the 6n log n, but we're still not where we want to be, which is 1 over e to the n log n. They're just off by a factor of 6 in the exponent. So again, the hardness results have improved dramatically, but we've also discovered barriers implying that new techniques will be needed to improve them any further. Okay, so even though, like, for example, the difference between e to the 6 log n seems very similar to e to the n log n from a complexity theory point of view, it might actually require very new techniques to make this improvement. Okay. Okay, great. So now I want to talk about something completely different, which is the hardness of benchmarks. So far we've been modeling all of the error of our sampler in terms of total closeness, constant closeness and total variation distance. Well, this is very limiting for at least 2 reasons. So one, experimentally, in reality, total variation distance is really difficult to measure. Right? There are lots of sort of sample complexity theoretic lower bounds that say, if you give me sort of a black box that's spitting out samples from some unknown distribution, then even to sort of test very modest properties of this black box, like is it close or far to the uniform distribution in total variation distance, is an exponentially hard problem. It takes an exponential number of samples. So in general, closeness and total variation distance is not something we can hope to verify with a polynomial number of samples. Theoretically, it doesn't have to bother us. In actuality, that's a big problem. Okay? And then the second thing I would say, which I sort of mentioned earlier, is that I don't think of closeness and total variation distance as a good proxy for physical noise. Right? In particular, what it means is that as the system size grows, the error doesn't change. And if you're ever talk to any experimentalist, you'll realize that if they're sort of increasing their system size and they're not changing their error, it's kind of ridiculous that the error shouldn't change. Okay? And so there's this question, is there a quantum signal, other than closeness in TVD to the ideal output distribution, that's sort of easier to verify and implement, okay, with an experiment? And so, there are other candidates, and I call them benchmarks. They generally rely on the following property of random quantum circuits, which we call the Porter-Thomas property. And what that says is that each output probability is exponentially distributed. Or more formally, if we look at the probability over the choice of random circuit, that a fixed outcome probability, like the probability of all zeros, is equal to q over 2 to the n, that probability scales like e to the minus q. Okay? That's called Porter-Thomas property. This is provably true for Haar random unitaries, and what it amounts there is very simple. It's just saying if you have a truly Haar random unitary and you ask, how is each entry distributed? Well, the answer is Gaussian, right? And if we're taking the square of that entry, we end up with an exponential distribution. Okay, that's essentially what Porter-Thomas is. Now, it's conjectured to be true even for shallow depth random circuits, but we don't know that. Okay, we have numerical evidence, but strictly speaking, it's a conjecture that even with a reasonably shallow depth, like say a log depth random quantum circuit, we end up converging to something like a Porter-Thomas distribution in our output amplitudes. Now, but what's important for us about this Porter-Thomas property is that it sort of implies that the output distribution of a random but fixed circuit is sort of, it's somewhat flat, but it's not uniform, right? So what do I mean by flat? Well, it sort of means that most of the output probabilities are going to be pretty close to 1 over 2 to the n, right? But some of them will be a little bit heavier, like a constant greater than 1 times 1 over 2 to the n. Some will be a little bit lighter. And so, it's sort of natural to ask the following observation. Well, one thing you can do if you can get access to the quantum circuit quantumly and you can sample from it, right? Well, then when you measure all n qubits in the standard basis, you should tend to see somewhat heavy outcomes, right? Outcomes that occur with heavier than average probability, right? Because you're able to sample. How difficult is identifying heavy samples, or heavy outcomes rather, classically? Could it be that a classical algorithm has a very difficult time? If I just give it the description of the quantum circuit, we don't believe the classical algorithm can sample from the output distribution. So could it be that this is a hard problem? Okay. And this is exactly the intuition behind the so-called heavy output generation problem due to Aronson and Chen from 2017. So here's a definition. With respect to a circuit C, they call an outcome X heavy if the probability of that outcome is greater than median in the output distribution of the circuit. So what is median? Well, if we're thinking about the output state as a probability vector with 2 to the n, probabilities, we just sort of sort it from largest to smallest, and we take the middle entry, and that's the median. Okay? Now, this Hogg problem measures this directly, a Hogg for heavy output generation. It's the following computational problem. We're given a random quantum circuit C. We want to output strings x1, x2 through xk such that at least 2/3 of them are heavy in the output distribution of C. Okay? That's what we call Hogg. And this is an easy problem quantumly for essentially obvious reasons, which is that if we can sample from the output distribution, right, we can just repeatedly run the circuit on the all zero state, keep taking measurements, and just using a Chernoff bound, it's easy to see that, actually, let me back up. So one thing we can show using the Porter-Thomas property is that the sum of probabilities that are above median in the output distribution is greater than 0.7. It's obvious that it's greater than or equal to half. And in fact, with Porter-Thomas, you can show it's actually a constant above a half. Because of this, it's now obvious to use a Chernoff bound to prove that if we keep sampling from the output distribution of this circuit, 2/3 of the outputs are heavy with high probability. Okay? So if you can sample from the output distribution of a random circuit, you can solve this heavy output generation problem. But the question is, Hogg still seems like a sampling task in some sense. We're not explicitly asking the classical algorithm to sample from the distribution, but we're sort of asking it to produce outcomes that sort of occur with heavy probability, which is not too far away from sampling. So the interesting question is, why should this problem, be hard classically, right? And so what Aronson and Chen prove, it's sort of their main result, is that one of their main results, is that Hogg is classically hard, assuming what they call the QIP conjecture. So QIP stands for quantum threshold assumption, and here's what it states. So it's that no efficient classical algorithm takes as input a random circuit C with a lot more gates than qubits, m is greater than n, and decides if a single output probability is heavy for that output distribution with probability something like 1/2 plus 1/2 to the n. Okay? So that's the conjecture. And what they show is that as long as QIP is true, then Hogg, this problem about outputting heavy samples, is also hard for a classical algorithm. Right. So now, have we made progress here? Right? It sort of seems like we've taken one problem that was kind of like a sampling problem, this Hogg problem, but we didn't really understand why it should be hard, and we've sort of reduced it from another problem, which seems a little bit non-standard, right? About sort of computing an estimate to the output probability of a random circuit, but that only works with exponentially small bias, right? Well, I think the reason that Aronson and Chen think that there's progress being made here when we consider QIP is that it seems a little bit closer to problems we understand, since it kind of involves the rough estimation of the output probability of the circuit. And, we've just spent the last, 30 minutes, an hour, or whatever, talking about those sorts of problems. I think from Aronson and Chen's perspective, this is a more natural problem since it involves this estimation as opposed to Hogg, which is more naturally like a sampling problem. Right? So the reason we're considering QIP is because we think we have better understanding for how powerful these sort of computation of output probabilities are than sort of sampling problems. Okay, and another key point is that this bias scales exponentially in the number of qubits rather than in the size. And that's really important because it turns out it's not hard to show a classical algorithm with a bias that scales exponentially in the size. So one way to do this is to sort of take the Feynman path integral. There's an exponential number of paths in the size of the circuit, m, right? And if you sort of randomly guess a small number of Feynman paths and then compare it to some threshold, you can actually show that this algorithm works to falsify Quoth, but it achieves bias 1 over 2 to the m, rather than 1 over 2 to the n. And so the whole reason we might believe this is true is because 1 over 2 to the n seems like it's something where there's no obvious algorithm. Okay? Okay, so now let me talk about the reduction. So how do we show that if this Quoth conjecture is true, then Hogg is hard? Actually, there's a really simple intuition, and the formal proof is just a little bit harder. Simple intuition is just, look, let's approach this by contrapositive. Let's assume that Hogg is easy, so we have a classical algorithm, right? Well then, okay, then what do we do? Well, we want to solve Quoth, right? So on input a random circuit, we can use our Hogg algorithm to produce heavy samples, right, a list of heavy samples, and then we're simply going to accept if that list includes the all zero string, and otherwise we're going to reject, right? In other words, we're going to say that all zero is heavy if we see it in our list of samples, and otherwise we'll reject, okay? It's not hard to see why this works, and in particular why we're getting this 2 to the minus n bias. The reason we're getting this 2 to the minus n bias is because there's even if 0 to the n is truly heavy, right? It's still exponentially small in n, right? So the chance that we happen to see it in our list of heavy outcomes is about 2 to the minus n. Okay? So that's why we're getting this very, very tiny bias. But the point is that tiny bias is still larger than the trivial algorithms, which are even smaller. Okay? I think I'm going to skip the more formal analysis, because at this point, it's a little bit formal. Okay, so now what I want to get to is that, at the end of the day, we're now at Google's experiments, 2019. Google decides not to use, they don't actually use the Hogg score as their benchmark. What they're more confident in is a different benchmark that they call linear cross entropy, or XEB for short. And it's based on their XEB score that they want to claim quantum advantage. So let me tell you about XEB. This is an alternative measure of heaviness. And it's really easy to define. If we think about it as a function of two distributions. One I'll call pexp. That's just the distribution over n-bit strings that the experiment is sampling from, right? Whatever distribution that is, we don't want to assume anything about it other than distribution is a black box outputting samples. The samples come from a distribution pexp. And then there's also p-ideal. That's the distribution. That's the ideal distribution of the random circuit if the algorithm made no error, if the experiment made no errors whatsoever. Okay, and then XEB is simply essentially a dot product of these two distributions, of the probabilities of these distributions, if you think of them as 2 to the n dimensional probability vectors, times this 2 to the n quantity, which is just normalization. It's not playing an important role. Okay? So it's literally 2 to the n times the sum over all inputs x, all outcomes x, of the probability of the experimental distribution at x times the probability of the ideal distribution at x. We can write this in another way as 2 to the n times the expectation of x drawn from the experimental distribution of the ideal distribution at x. Okay? And using the Porter-Thomas property, one thing we can see is if the experiment made no errors whatsoever and pexp is equal to p-ideal, then you can analytically compute that with high probability over a choice of circuit, the XEB should be 2. Okay? But if on the other hand, these two distributions were uncorrelated from each other, like for example, we were sampling from the uniform distribution, which is u in this equation, you can compute that you would get 1. Okay? So what does Google want to do? Google wants to compute their XEB score, which you can do sample efficiently. I'll discuss that in a moment. So they take a small number of samples from the device. They're going to compute their XEB score, and then they're going to accept if they think they're larger than 1. Okay, or ideally closer to 2. That's the goal. Okay, now what do we like about XEB? Well, what we really like about it is it can be well approximated in a small number of device samples via concentration of measure arguments. But it requires exponential time to compute the ideal probabilities of the observed samples. Okay, so in other words, what do we end up doing? This is what Google actually does. They take k samples from their device. We'll call it Z1, Z2 through Zk. For each one of those samples, they're holding the description of the random circuit in their hand. So on their supercomputer, they can compute the ideal output probability of seeing those samples. That's not an efficient computation. That takes an exponential amount of time. But the point is that they don't have to do it too many times. K, the number of samples here, can be small because this is a sample-efficient score. Okay, and I guess the reason that's true, by the way, boils down to the fact that Porter-Thomas is, or really that it has a bounded second moment, but more informally, the fact that it's a rather flat distribution. Right? That's what makes this task sample efficient, that there's not much difference between the largest output probability and the smallest output probability of a random circuit. Okay, great. So now there's this question, why is scoring well on cross-entropy classically hard? Right? So far we talked about the Hogg benchmark. We asked, why is Hogg classically hard? Well, because there is this Quoth conjecture, which you can believe or not believe, but the point is, assuming Quoth, Hogg is hard. Well, now there's this new task, which we call cross-entropy, which is, sampling from a distribution that scores higher than 1, say, on the cross-entropy benchmark. And we can ask, why is that hard for a classical computer? Okay, well, to do this, Aronson and Gunn first simplify the problem a little bit. They introduce a problem that they call XHOG, which is sort of, short for linear cross-entropy heavy output generation, sort of an intermediate problem between the Hogg problem and cross-entropy. And what it is the following. We're given as input a random circuit C. We want to output k distinct samples from the output distribution, Z1, Z2 through Zk, so that if we look at the average of the probabilities of each of those outcomes, that's greater than or equal to some number b over 2 to the n, where we think of b as 1 plus epsilon. Okay? Something larger than 1. Now, like we said before, by repeating a noiseless circuit, we'd be able to achieve b equal 2, so epsilon would equal to 1. That can be derived by this Porter-Thomas property of the distribution. But noise in the experiment can cause this circuit to output much smaller values of b. So in fact, in Google's experiment, the b that they got was 1.002. Okay, on its 53 qubit RCS experiment. Now, nonetheless, theoretically, this still seems like a sampling task, very much like Hogg. So why should this be hard classically? Well, what Aronson and Gunn in 2019 proposes, they say, well, very similarly to how Hogg, without the x, had a Quoth, XHogg has an X-Quoth. Okay, so what they show is that XHogg is hard, assuming the conjecture they call X-Quoth. Let me tell you what X-Quoth says, and this is really quite a daring conjecture in the sense that it's a very customized. It's very customized to the problem. I think without thinking about this, the way these problems sort of relate and the reductions, probably wouldn't have come up with this problem. So here's what it says. Let's start by saying no efficient classical algorithm given as input a random quantum circuit produces an estimate p to the output probability of that circuit so that the following is true. Now let me sort of talk you through this because it's not completely obvious what this means. Okay, so we're going to look at the following quantity, and what I'm going to claim is the quantity is, the way to think about this quantity is it's comparing two algorithms. One is an algorithm that simply outputs 1 over 2 to the n independent of the circuit. I'll call that the trivial algorithm. So it's given a circuit, it always outputs 1 over 2 to the n. And the second quantity refers to the error made by this algorithm that outputs an estimate p to p0, to the output probability. And what we're trying to say is if we measure these two algorithms, how well they score, by a sort of mean squared error, right? That's this sort of expectation of the square. That we're doing that there's no way to do a little bit better, and a little bit means anything greater than 2 to the minus n, over the algorithm that's trivial and outputs 1 over 2 to the n regardless of the input. Okay, so that's what this algorithm is saying. It's really comparing two different algorithms and saying that, there's no way to do even a little bit better than the trivial algorithm, which given a random quantum circuit always outputs 1 over 2 to the n. Okay, or summarized, no classical algorithm can achieve a mean squared error at estimating an output probability of a random quantum circuit that's even slightly better than the trivial algorithm that always outputs 2 to the minus n. Okay, and xquath implies xhog is hard by very similar reduction. So what is the idea? Well, we assume that there's an xhog algorithm, this is like the contrapositive, that outputs samples z1, z2 through zk, so that the average probability of those samples is equal to b over 2 to the n, right? Then what we do is we look, is 0 to the n, is the all zero outcome on the list or is it not? If it is, we output b over 2 to the n as an estimate to the all zeros probability. Otherwise, we output 1 over 2 to the n. Okay, so let me end with just a few comments, and then I'll stop for questions. So one thing I think to notice is that it's a very lossy reduction. And what do I mean by that? Well, the problem that the quantum algorithm is actually solving, like the Hog problem or the xhog problem, that problem, it might be hard, it might be easy, we don't know. But one thing that does seem to be true is that once we reduce this problem to the quath variant, like the xquath variant, it seems like we're losing quite a bit. Right? We're losing quite a bit because the probability that we even see the outcome on the list is already exponentially small. Right? So, it would be very interesting to see if this could be improved, whether or not there's some way of avoiding this sort of exponential bias when you reduce, one problem to the other. I think the other thing I want to say, maybe with a more physical mindset, is one reason that the XEB score is really interesting is it turns out that it actually well approximates the fidelity, the circuit fidelity of the noisy experiment. So it actually gives us a sample efficient way of estimating fidelity. Now, because of that, it's useful for benchmarking. In fact, my group has a lot of papers about how we can benchmark very large quantum systems, maybe not even random circuits, with this XEB score. On the other hand, we need to make certain assumptions about the noise for the XEB score to correlate with the fidelity. And roughly speaking, those assumptions tend to have to do with the noise rate being sufficiently small. Okay? So if it's sufficiently small, like say 1 over the system size, we think XEB is actually a pretty good proxy for fidelity. If it's large, if it's a constant, as the system size scales, it's probably a rather bad estimate for fidelity. It's kind of a high-level picture. Let me take some questions about this.
So a quick question about the Porter-Thomas distribution.
Yeah.
You said it's believed that shallow circuits also give rise to this distribution.
Yeah.
Did you say that was log or polylog?
Good question. Well, it's not really known either way, so it's not exactly clear where the conjecture should be. I've certainly heard it conjecture that it's true at log. Certainly, deeper that you get, the more likely this conjecture is to be true, right? But strictly speaking, I haven't seen a proof at any depth that's not, that doesn't, clearly approximate any depth shallower than some polynomial, let's say.
Hi, thank you so much. You've talked about different benchmarks, the cross entropy versus Hog. I'm just wondering how you can talk about benchmarks in isolation from the problem, because if you make the benchmark easier to verify, and as you said with XEB, like that uses fewer samples, then wouldn't that make it easier to classically simulate? Just a high-level question that I had.
Well, okay, I'm not exactly sure I understand the question, but I think the point is that XEB gives a benchmark, and all I mean by benchmark here is it's very simple. It's just it's given a quantum experiment, output and some samples, output some number, right? And what I say, for example, when I say something like XEB correlates with fidelity, is just that that number also happens to be related to the fidelity of the experiment. So in that sense, it's a benchmark. I don't really know in what sense it's independent of the problem, but I'm happy to keep it.
I guess my feeling was you're talking about checking whether the quantum algorithm, whether the quantum sampling task has been successfully run. And if you can now check that with fewer samples, does that not maybe make it easier for you to produce those samples? Because you need to get fewer things right in a sense? I mean, I'm seeing this at a pretty high level, so
yeah,
maybe I'm missing something.
I mean, maybe I see it at a very high level where you're going. I don't know of a formal relation like that. You know, it's not at all clear that that's true. It is sample efficient. It's not clear if that has anything to do with the classical difficulty. Yeah.
Hi, could you quickly review again the relation between the cross entropy itself and X-hog and whether the claim about cross entropy calculation being hard relies on the X-quoth assumption as well?
Yeah, that's a great question. So, you know, as far as I know, these are sort of two separate problems, but the reason you would believe one is hard is the same as the reason you would believe the other is hard, right? So what is that really saying? So let's go back and let's look at the, oops, sorry, I'm using the wrong button. Let's go back and let's look at the definition. Okay, so what is X-hog really saying? Why would you believe this is hard? Well, what X-hog is saying is that sort of outputting sufficiently heavy outcomes in the output distribution is a hard problem. Okay, that's very clear. You're just taking some number of samples. For each sample, you're computing the ideal output probability, and you accept if it's sufficiently high, right? Now, let's look at what XEB is. You know, what does it mean to get a high XEB score? Well, I think what a high XEB score is saying somehow is that these two distributions, the experimental distribution and the ideal distribution, they sort of match up nicely. You know, distributions, pairs of distributions that score well on the XEB benchmark, they sort of have a lot of shared heavy elements in common, right? That's really what it's measuring. Right? It's not hard to see that that's exactly what this formula is saying. If you look at, you know, from the expectation point of view, you look at this experimental distribution, mostly you're going to see sort of somewhat heavy, you know, outputs from the experiment when you sample from the experiment. And then what we do is we just calculate the corresponding, you know, ideal probability, and we accept if that's sufficiently high. So in that case, I would say these two quantities are sort of measuring the same thing. That's not to say that there's like, you know, a particularly formal relationship between the two of them, other than I think they're just measuring the same thing.
Hi, is the Porter-Thomas distribution you mentioned, is it related to the anti-concentration property?
Yeah, good. No, we don't know that. We don't know that to be true. In fact, one thing that's interesting is that anti-concentration is a property of a random circuit distribution that would be true even if you match a small number of moments of the Haar measure. So, or another way of saying it, it would be true even if you only have a t design for a small t. So I think you get anti-concentration at approximate 2 design, something like this. That's not true for Porter-Thomas. So in fact, Porter-Thomas is not a low moment property of a random circuit. Because of that, I don't think they're, you know, they're sort of somewhat different, I think. Yeah.
Thank you. On your, when you mentioned that linear cross entropy could be well approximated in a few device samples, you mentioned that this is due to concentration of measure arguments. Could you spell out more, in more detail, what is the intuition behind these arguments?
Oh yeah, okay. So I only gave an intuition. I didn't give a proof. It's, you know, the idea is that we can use this property of the Porter-Thomas distribution, which is that it's reasonably flat, you know, to show that these sort of and again, formally the argument has to do with bounded second moments. We're not really going into that. I'm not going to show the inequalities that you use to show this, but the intuition is pretty clear. It's that, you know, this distribution is really flat, so most of the probabilities are similar to other probabilities, and therefore, you know, if you're just going to sample from this, you know, you're going to make a small number of samples from the device and use those samples to then compute this benchmark, you know, the number of the score that you get when you make a small number of samples shouldn't really change very much if you make a much larger number of samples, because the distribution is flat. It doesn't have a great variance in the first place. You can formalize that. It's not so hard, but we're not going to do that right now. Yeah.
Okay, thank you.
I would like to ask two questions actually. First one is, usually in variational quantum computing, depolarizing channels and this kind of open system noise has really a killing factor for this kind of computation. Is the problem is this problem of depolarizing channels also impacts the kind of computations? Meaning that it will be a killing factor for showing this gap between classical and quantum computing?
So I think I missed. Can you say very quickly what was the question? I think I can't quite hear.
Is, for example, the polarizing channel noise type of the polarizing channel a killing factor for this type of proof of gap between classical and quantum computing?
Is noise a factor in the proof? What sort of factor?
So if we want to show that quantum computing is overall better than classical computing.
Is better? Yes, I agree with that.
If there will be depolarizing channel, say even with this small probability of going to identity, will be a killing factor for this type of proofs supremacy.
I mean, we don't know, right? We don't know. That's what we don't know. Sort of what sorts of scores should we accept and conclude quantum, and what sorts of scores are too low, right? We don't have a good feeling for that.
And second very quick question, probably you don't, I'm not sure if you can tell us. I know that Google is very interested, of course, in showing this type of supremacy, but also we have another big company, which is IBM, which I'm not sure if they are also trying to show it this way. Do you know if there's any good scientific reason for them of like this?
Well, okay. Here's what I'm going to say. I don't think IBM has, publicly said that they're interested in quantum supremacy, at least not to the best of my knowledge. What I do know is that they do have a quantum volume benchmark, right, which has a very similar intuition to XEB. Okay, it's not the same as XEB, to be clear, but it's very similar. So they're doing similar things. They're not necessarily they're not sticking their neck out and saying if we achieve a certain score on the benchmark, then it's hard. But they're definitely interested in using very similar benchmarks as a benchmark to understand things like fidelity, for example, which otherwise would be very hard to understand. Yeah.
Thank you.
Hi. I have another question, which is about at some point you started talking about outputting probabilities. So the task is to sample, but then I think at some point you were talking a lot about like outputting the probability itself. So what was that? What was the general logic of introducing that?
Yeah, that's a great question. So there's sort of two things that you can ask. So one is, you have these benchmarks, and in principle, you can, if you sample, you can say that, theoretically you score well. If you sample from the ideal distribution or a distribution close to that distribution, you can say that you score well on those benchmarks. But another question is, how, if you're an experimentalist and you just get the samples, how do you actually compute these benchmarks, right? And the answer to that is a little bit unfortunate. The answer is that you actually, explicitly compute ideal probabilities of the samples that you see, right? So in other words, how does Google know that they achieved a 1 point, whatever score on XEB? Well, they know that because they looked, they observed certain samples, and then based on the samples that they observed, they used a classical supercomputer to compute the ideal probability of seeing those samples, right? And that's what then gave them their score, right? So, theoretically, you can talk about the hardness of scoring above a certain amount on one of these benchmarks, but when it actually comes down to, in the experiment, scoring what they got from the observed samples, you end up computing output probabilities to do that. So that's not an efficient classical task. Yeah.
I got a question about significant digits. So you said that Google got a 1.002 score.
Yeah.
I guess what's the limit on the amount of digits you can have until you don't have an advantage anymore?
Yeah, that's a good question. Or maybe what you're really asking is, why would we think that 0.002 or whatever was impressive or quantum? I sort of have two answers to that. So one is that if you think about it asymptotically, if you maintained your 0.02 score, that would be really quite something, actually. That'd be a constant score in a complexity theoretic statement. But that's not actually what they're doing. In fact, with uncorrected noise, they would very much expect that, they're 0.02 now at 53 qubits, and at 54 qubits, they're actually much worse. 55 qubits, much worse, and so on. So, the question is, why would scoring 0.02 be so important? I think the honest answer is that's not a question about complexity theory. That's a question about how fast current classical simulation algorithms that may not be efficient as n scales, but how well those can work to simulate, to score 0.002 on a 53-qubit random circuit experiment. And Google went through all of those that they knew of at the time, and they concluded that those algorithms, those classical algorithms, would take a long amount of human time to score 0.02, right? But there's not a lot of complexity theoretic basis for that particular number, right? Complexity theory is all about scaling, and it's very clear that their scaling would not have been so good. It would have been exponentially scaling if they had increased their system size without decreasing their noise rate.
Oh, thank you.
Just a question about, because so far you assume some sort of independent sampling. I think that the sample must be independently sampled, and can we say something if the samples are not in the IID setting?
Yeah, that's a great question. We're definitely assuming that at the moment, that it's IID. That's sort of an oversimplification. There are results that say that even if you have correlated samples, you can still use some of these benchmarks, but the statistics there is a little bit more murky, and depending on what you mean, you can sometimes get a proof and sometimes not. Yeah.
Hello. So my question, I'm here. Yeah, my question is about understanding a little bit more the connection with the, in the beginning of your presentation, you talked about the fact, if I understood correctly, that we are almost showing that the average sampling, the classically performing the average sampling, we are almost having the proof that it's hard.
Yeah.
And I would just like to understand, so the connection with the, let's say, so for instance, you have a depolarizing channel on each of the physical qubit in your hardware. What will be it will still not show that it is hard to, let's say that with a depolarizing channel, the quantum computer will outperform the classical one, even if you had the complete proof for the average.
Right.
So what is the connection?
No, that's good. It may be a great way to end this talk. So here's the thing. So far, we haven't actually been addressing physical noise. Now, if I had a lot more time, I would have gone through arguments that would have talked about how hard the problem is with physical noise, and in some cases it becomes easy, in some cases not. But all of the discussion that I had about the hardness of simulating random quantum circuits, that was all modeling sort of, I don't even want to call it noise. Let's say imperfection only in one sense, which is closeness and total variation distance. So then you should ask, if you have a physical experiment and it has depolarizing noise, for example, like how does the total variation distance, scale? Well, actually it quickly becomes very large. It quickly becomes 1, like the highest, total variation distance you possibly can have. So it's definitely not the case that, constant total variation distance is a good model of physical noise. So the only thing that you really get from the complexity theoretic arguments is just to say that, in principle, if you implemented the circuit perfectly, that would be a hard problem, right? And then after that, what you do is you look at the noisy experiment and you sort of say, well, we know that there's hardness there if it was implemented perfectly. We hope that the noise didn't destroy too much of the signal, right? And so do we know of any classical algorithms that can take advantage of that noise to simulate the experiment? Maybe not efficiently, but in a running time that's comparable to the experiment. So far, the answer is no. We have not been able to see for the largest size quantum experiment that the classical runtime of the best simulation algorithm is competitive. But like I said in the very beginning, it's always going to be a competition between the best classical algorithms and the best experiments. Yeah.
Okay, thank you.
Yeah. The 2/3 ratio, where did that come from? So you mean the fact that we should get, are you talking about like Hogg, the fact that we have 2/3 of the outcomes that are heavy, or okay, no, that's So first of all, that number is not very important as long as it's a constant larger than a half. We just end up using a Chernoff bound to get that. And it's just, I mean, that's exactly what it is. It's just saying, look, if you're outputting samples from the exact, the ideal distribution of a random circuit, I can't guarantee you that every single sample that I output is going to be heavy. Sometimes I might output a light sample, but most of the time, it's going to be heavy. That's all it's saying. Yeah, there's nothing physical about that. Okay, so it looks like I didn't get time to go into my classical algorithms. Hopefully, though, we can post the slides somewhere, and if you want to read more about it, you can. And so at the moment, we have a very optimistic picture. Everything is hard. Not actually the case. There's a lot of new classical algorithms that are very easy. They're very interesting and show easiness. Thanks a lot.